All right, let's jump right in. We're talking about something that holds both incredible promise and, let's be honest, some serious challenges: nuclear power. This is the kind of energy that could literally reshape our future, so let's get into it. I mean, this is the big question of our time, right? How do we power this whole world of ours without relying on fossil fuels? Everything we do runs on energy, but the way we've been getting it is, well, it's warming the planet. So what's the alternative? Where do we find clean, reliable power? Yeah, it turns out there is a mind-boggling amount of energy locked away inside the tiniest things imaginable, the atoms that make up everything. So the key, is figuring out how to get it out. And in this explainer, we're going to look at the two main ways we figured out how to do just that: fission and fusion. Okay, so here's our game plan. First, we'll cover the basics of unlocking atomic energy. Then, we'll really dig into the fission chain reaction. After that, we're going to take a peek inside a nuclear reactor and then talk about the high-stakes trade-offs. And finally, we'll look to the future with the promise of fusion. Let's do it. So at its core, the whole concept is actually pretty simple. You've got the nucleus, right, the very center of an atom, and it turns out it holds a massive amount of energy. To unleash that power, we really have two options. We can either split a big nucleus apart, or we can smash two small ones together. All right, let's start with fission. This is the method we're actually using in power plants today, and it's all about splitting things apart. But here's the thing. The real secret sauce isn't just splitting one atom. Nope. It's about setting off a self-sustaining cascade, a tidal wave of energy. So what does that actually mean? Well, basically, you take a big, heavy nucleus, something like uranium-235, and you split it. Now, that split releases a burst of energy, which is great. But what's even more important is that it also shoots out a couple of extra neutrons. And trust me, those little neutrons are the key to this whole thing. The best way to picture this is like a line of dominoes. Seriously, it all kicks off with one single trigger. A slow-moving neutron comes along and gets absorbed by a uranium nucleus. That makes the nucleus super unstable and split. It breaks into two smaller pieces. But here's the kicker, the part that makes it a chain reaction. That split releases 2 or 3 new neutrons, which then zoom off and hit other uranium nuclei, which then split and release more neutrons. And you can see where this is going. It's a cascade. So a chain reaction like that is obviously incredibly powerful. But how do you harness it? How do you control it to generate electricity instead of it being a bomb? That's where the nuclear reactor comes into play. Let's take a guided tour, shall we? Inside a reactor, you've got several key parts all working in concert. We're going to look at the big 5 here, and each one plays an absolutely critical role in starting, sustaining, and, most importantly, safely controlling that fission reaction. Okay, first up, the nuclear fuel rods. This is where the action is. These rods are packed with the stuff that's going to split, usually uranium or plutonium. And they're arranged really carefully so that the neutrons can travel from one rod to the next, almost like passing a torch to keep that chain reaction going. Now, this next part is pretty ingenious. See, the neutrons that get released during fission are flying around way too fast. They're too zippy to get captured by other uranium atoms. So you have the moderator, often a big core of graphite, and it acts like a speed bump. It slows those neutrons down to just the right speed so they can be absorbed and keep the reaction chugging along. Okay, so if the moderator is kind of like the gas pedal, then the control rods are definitely the brakes. These are made of a material that just loves to soak up neutrons. So you can lower them into the reactor to absorb excess neutrons and slow the reaction down, or you can raise them up to speed things up. This is exactly how you fine-tune the power output. So with all this atom splitting going on, you can imagine it generates an immense amount of heat. That's where the coolant comes in. Its job is to absorb all that heat and carry it away. And what does it do with it? It boils water. That's right. It boils water to create high-pressure steam. That steam spins a turbine, and that turbine drives a generator to make electricity. It's a really, really high-tech way to boil water. And this right here is why all those control systems are so absolutely vital. When you think about it, an uncontrolled fission reaction is the very basis of an atomic bomb. That really puts it all into perspective, doesn't it? The only thing separating a power plant from a weapon is control. So, as you can probably guess, this incredible power source comes with a pretty serious list of pros and cons. It's not a simple issue. So let's break down this high-stakes trade-off that sits right at the very heart of the whole nuclear debate. Okay, let's look at the two sides of the coin here. On the plus side, the advantages are huge. Nuclear power produces zero polluting gases, it doesn't contribute to global warming, the fuel costs are super low, and you don't need much of it, which is great for the environment. But then you look at the other side. The waste it produces is radioactive for thousands of years. A large-scale accident, though rare, can be catastrophic. And the cost to build these plants and then take them down safely is astronomical. It's a tough balance. And, this really boils it all down to the core dilemma. The benefit? We get clean air today, no polluting gases. That is a massive win for our planet. But the drawback? The lasting legacy is that we're creating radioactive waste that will be dangerous for literally thousands and thousands of years, longer than all of recorded human history. That's a heavy trade-off. But wait. Fission isn't the only game in town. There is another type of nuclear energy out there, one that powers our sun and, well, every single star in the universe. And that is nuclear fusion. So what's the difference? It actually comes down to a really simple distinction. Fission is all about splitting a large nucleus apart. It's division. Fusion, on the other hand, is about joining two small nuclei together. It's addition. Instead of breaking a big atom, you're taking two tiny ones, like hydrogen, and forcing them to become one. And just like with fission, this process releases an absolutely staggering amount of energy. A tiny, tiny bit of mass gets converted directly into pure energy. And get this, that's literally what sunshine is. It's the energy from fusion reactions happening 93 million miles away in our sun. Okay, so this sounds amazing, right? Even more energy, less dangerous waste. It sounds like the perfect solution. So what's the catch? Why aren't all of our cities powered by a little mini sun in a box? Well, here's the catch, and yeah, it's a big one. You see, atomic nuclei are all positively charged, which means they naturally repel each other. They push each other away. To force them to fuse, you need some seriously extreme conditions. We're talking temperatures between 100 and 200 million degrees Celsius. That is many, many times hotter than the actual core of the sun. And that, in a nutshell, is where we are with fusion today. Scientists have done it. They've successfully achieved fusion in experiments. But building a reactor that can sustain those insane temperatures and actually generate more energy than it takes to run it, all while being financially viable, well, that is one of the greatest scientific and engineering challenges we have ever faced. And that brings us full circle. On one hand, we have fission, a powerful tool that's available to us right now, but it comes with some very serious, very long-term consequences. And on the other hand, we have fusion, the dream, really, of limitless, clean energy, if we can just figure out how to build a bottle that can hold a star. In this urgent race for clean energy, the question remains, which path do we take? And is the reward truly worth the risk?